Classification algorithms, so many models, so little time. How do you pick the right one? If you've ever felt lost trying to figure out which algorithm gives the best performance on your dataset, this video is exactly what you need. We're taking one dataset, running it through multiple classification models, and comparing their results side by side, so you'll know which one actually works best for your project. It's code-heavy, result-driven, and packed with actionable insights. Welcome to day 15 of the 30 Days of Machine Learning series. If you're just joining, don't worry. You can click right here to access the full playlist and catch up on every step of the journey so far. And hey, make sure to hit that subscribe button so the next video in this series drives straight into your feed. We start by importing pandas, NumPy, matplotlib, and Seaborn, our essential libraries for data manipulation, numerical operations, and stunning visualizations. Loading our training data with pandas, then using head to peek at the first few rows. Checking the dataset size with shape, listing feature names with columns, and summarizing statistics using describe for quick insights. Using info to review data types and non-null counts, then isNull sum. Creating a heat map with Seaborn to visually highlight missing values in the dataset using a striking magma color palette. Counting how many passengers survived using valued counts. Then calculating survival rates to understand the proportion of survivors and non-survivors in percentages. Setting Seaborn's style to white grid for clean, visually appealing plots with grid lines for better readability and enhanced presentation. Creating a count plot to visualize the number of survivors and non-survivors, using the Set2 color palette for a fresh, vibrant look. Visualizing the distribution of passengers across different classes with a count plot, using the bold Set1 color palette for clarity. Now, let's break down survival rates by class with a count plot, using the Cool Warm palette to highlight differences effectively. Plotting a histogram of ages with 30 bins, adding a KDE curve for smooth distribution, and coloring it blue for clarity. Let's explore survival by gender with a count plot, using the vibrant HueSil palette to clearly differentiate between survivors and non-survivors. Calculating the mode, median, and mean of age to understand its central distribution. Filling missing age values with the median to ensure no gaps, then displaying the updated dataset. Rechecking for missing values with a heat map, ensuring no gaps remain after filling missing age data. Creating a scatter plot to visualize the relationship between age and fare, with survival status color-coded for better insight. Importing label encoder from scikit-learn to convert categorical labels into numerical values for machine learning models. Encoding passenger names into numerical values for model compatibility, then decoding them back to check the transformed labels. Transforming name and sex columns using label encoder to prepare for modeling, then filling missing embarked values with Q and encoding it. This ensures all categorical data is numerically represented for the model to process effectively. creating a heat map to visualize correlations between features in the dataset, using the RDBU color palette for clear, intuitive insights. Displaying the dataset before and after, dropping irrelevant columns like passenger ride, ticket, and cabin to clean up the data for modeling. Importing Select K-Best and Chai2 from scikit-learn to perform feature selection, helping us choose the most important features for our model. Selecting features and target to prepare for model training. Here, we apply Select K-Best with the chi-squared test to select the top 8 features that have the strongest relationship with our target variable, survived. After fitting the model, we display the feature scores, highlighting the most important columns for prediction. This step helps ensure that we're using the most relevant data for training our model. Displaying the dataset before and after, dropping unnecessary columns like embarked, SIBSP, and parch for cleaner model input. We're scaling the selected features, P-class, sex, name, and fare, using standard scaler to standardize the data. This ensures all features are on the same scale, making our model training more efficient and improving accuracy. The target, survived, remains unchanged for model predictions. Splitting the dataset into training and testing sets, with 25% allocated for testing, ensuring our model can be trained and evaluated on separate data for better performance assessment. Importing evaluation metrics, accuracy, ROC-AUC, and cross-validation to assess model performance comprehensively. This function allows us to train a classifier and evaluate its performance using multiple metrics. First, it fits the classifier on the training data and predicts the outcomes on the test set. It then calculates the accuracy score, showing how many predictions were correct. The ROC-AUC score is used to assess the classifier's ability to distinguish between the classes. Finally, the function computes the cross-validation score using tenfold cross-validation to measure how consistent the model's performance is across different subsets of the training data. This approach gives a comprehensive understanding of a classifier's overall effectiveness and reliability. The model evaluation function evaluates a classifier's performance using the confusion matrix and several additional metrics. It starts by calculating the confusion matrix using the true labels and the predicted labels. Then, it generates labels for the confusion matrix that include the actual counts and the corresponding percentages for each class: true negatives, false positives, false negatives, and true positives. These labels are formatted and displayed on the heat map for better clarity. Next, it calculates precision and recall, important metrics in classification tasks. Precision measures the accuracy of positive predictions, while recall evaluates how well the classifier identifies actual positive instances. Finally, it prints out both metrics. This function helps you not only visualize the classifier's performance, but also provides essential evaluation metrics to judge its effectiveness. The grid search function performs hyperparameter tuning using grid search CV to find the best combination of parameters for a classifier. It evaluates multiple parameter settings with tenfold cross-validation, selecting the one with the highest accuracy. After fitting the model, it prints the highest accuracy and the corresponding best parameters, helping optimize model performance by finding the ideal settings. Initializing a logistic regression model with a fixed random state, L2 regularization, and a regularization strength of 10 to balance performance and prevent overfitting. Training and evaluating the logistic regression model using accuracy, ROCAUC, confusion matrix, precision, and recall. Here, we're initializing a support vector classifier, SVC, with a linear kernel and a regularization parameter C equals 0.1, controlling overfitting while maintaining model flexibility. Performing grid search to find the best C value for the SVC model using cross-validation. Training and evaluating the SVC model, assessing accuracy, ROCAUC, confusion matrix, precision, and recall. Initializing a decision tree classifier with the entropy criterion to optimize decision-making based on information gain. Training and evaluating the decision tree classifier, checking accuracy, ROCAUC, confusion matrix, precision, and recall. Here, we're initializing a random forest classifier with a maximum depth of 2 to control model complexity, along with a fixed random state for reproducibility. Training and evaluating the random forest classifier, checking accuracy, ROCAUC, confusion matrix, precision, and recall. Initializing a k-nearest neighbors classifier with 3 neighbors, leaf size 7, and Manhattan distance metric. We're defining a range of hyperparameters for the k-nearest neighbors classifier, including leaf sizes, the number of neighbors, and distance metrics, Manhattan and Euclidean. Using grid search CV, we search through these combinations to find the best performing hyperparameters, optimizing the model's performance for the dataset. Training and evaluating the k-nearest neighbors classifier, assessing accuracy, ROC-AUC, confusion matrix, precision, and recall. We've compiled a dictionary to compare the cross-validation scores of different models, including logistic regression, SVM, decision tree, random forest, and k-nearest neighbors. This helps us evaluate which model performs best based on their average performance across multiple folds, guiding our selection for the most effective classifier. By converting the model's dictionary into a data frame, we can easily compare the cross-validation scores. As we can see, the support vector machines, SVM model, achieved the highest cross-validation score at 0.7919, outperforming the other models in terms of consistency and accuracy across different subsets of data. In conclusion, we've compared several supervised classification models and found that SVM performed the best with the highest cross-validation score. But this is just the beginning. In the next video, we'll dive into supervised regression, where we'll explore how to predict continuous values and fine-tune regression models. Click on the screen to continue to the next video and take your machine learning skills to the next level.